Hey guys! So last time we were able to determine an equation for delta h, the error in the height of your girlfriend, given some delta d and delta theta. The equation is just right up here if you forgot. But then as engineers, what we want to do often is we want to minimize the error associated with our measurements. So in this case, we want to minimize delta h. So how do you do that? Well, in this example, there's three ways you can do it. The first two are pretty simple. You can minimize delta theta and delta d. But the third way is that you can also stand a certain distance from the structure that you're measuring the height of. What happens is that there's a certain optimal distance at which you can stand to minimize your delta h. And this will come in handy for your guys' lab that you guys are going to do pretty soon. So you guys know how far-ish from your structure to stand to measure the height of it. So in these kinds of optimization problems, the first thing we want to do is we want to make this equation as simple as possible. And in these problems, the last thing you want on your hands is a trig term, like tangent. Also, we notice that the right side of this equation has two variables. If we assume some delta theta and delta d, we still have a theta and a d here to worry about. Two variables at the same time usually isn't very awesome. So what we can do is that we can substitute in for tangent of theta. If we notice that when we rearrange this equation for tangent of theta, we get over here tangent of theta equals h over d. The critical thing to notice is that h is not a variable actually. It will remain constant in one measurement. That is that although that you can measure the heights of different things and the h will be changing for that, in one scenario, h will not be changing. It will be a constant. So therefore, if we substitute this thing in, and we have some sort of assumed value for delta theta and delta d, as we see over here, we can have an equation with only one variable and a bunch of constants. So let's go ahead and do that. So here we have delta h is going to be equal to d times delta theta, nothing changed there, plus delta d, and instead of tangent of theta, we're going to have h over d, plus d delta theta, and then we have to square this term, h over d, entire thing squared. This is going to be over 1 minus delta theta times h over d. All right, so we can clean this up a bit if we do some stuff to the denominator. We see here that we have a lot of things over d, so we can try to get rid of that. So delta h here is going to be equal to, let's say we multiply this entire bottom by d, and we do the same thing to the top. It'll make this equation a little more user-friendly. So multiplying the top by d, we get d squared delta theta plus delta d times h plus these d's will cancel out. So you'll be just left with delta theta times h squared. This entire thing is going to be over this denominator multiplied by d. So this will become d minus delta theta times h. Cool. So far, just to recap, we have an equation. This is the same equation. I haven't really done anything new to it except for making a single substitution and cleaning this thing up. So we have here on delta h equals this thing. We can assume that for this scenario, we have a delta theta that's fixed and a delta d that's fixed, given by these values up here. I've set delta d here equal to 0.1 meters and delta theta equal to 1 degree, which is also equal to approximately 0.0175 radians. So this is going to be constant. This is going to be constant. The height's not going to change. We have a constant, and we have a constant times a constant. This over here is also constant. And the last constant over here. Sorry. All right, so that means we have an equation with a single variable on the right-hand side. So then now what we can do is this part can get a little bit tricky. What we want to do is we can choose various values of h as a constant here. And then for each one of those, we can plot a graph of delta h versus d. We can then find, using some sort of, you can use a graphing calculator for this actually, or Excel can do it pretty nicely also. And we will find a minimum for each graph of delta h versus d of constant h. So let's say we set h equal to, say, 50, right? For this, our graph is going to look something like this, where at first it will spike up because of the denominator. You'll have an asymptote. And then it quickly drops back down to some sort of minimum. And it is this d minimum here that we're interested in. So for h equals 50, I just plug this thing into my graphing calculator, and I found that the minimal d, given these approximations for delta theta and delta d, comes out to be about 53 meters. So if your structure is about 50 meters tall, given these kinds of errors, you want to stand about 53 meters away from your object to measure the height of it, to get the minimal error. Repeating this for 75, 100, and even 2,000 meters, I got the following numbers. Since we have some sort of h and some sort of d, what we can do is we can back out the theta measurements from this. And by plugging this thing back into this equation here, I was able to get the following values of theta. So this is the minimal angle. This is the angle of which you'll get the minimal delta h. You'll have the lowest error. And so what do we notice about these? Well, all of these things are kind of a little bit less than 45 degrees, but approximately equal to 45 degrees. So this means that when you're taking your height measurements for the lab that's coming up, you want to make sure that regardless of what kind of error you have, you want to make sure that the angle from the ground to the top of the structure, let's say this is your structure, this angle here is going to be about 45 degrees. That will minimize the error that you have, regardless of your delta theta and delta d, right? So this was a little bit assumption intensive in a certain way. We assumed various values of h to back out different values of theta minimum over there, which we then use to make a generalization. Generalization being, if we want to have a minimal delta h, have your height be approximately 45 degrees, right? Well, that's it for this time. Good luck with the lab, and I'll see you guys next time.